So thanks for Diego for coming here, and he's going to give a talk on Raft, a consensus protocol on the lines of Paxos and Zab. He's been working on this with Professor John Hosterhout for the last, like I don't know,
2 years.
2 years. He's just finished his PhD recently. I think we should just give him a round of applause for that. So over to you.
Thanks. I'll just jump right in. So I'm going to go over kind of an intro to consensus and then deeper on the Raft algorithm itself. What is consensus? It's a bit hard to define, but it's agreement on shared state. So you have multiple servers. You want them to kind of agree and present a consistent view of some state, and yet you want to be able to tolerate failures. So a typical consensus cluster can recover from server failures autonomously. Like here in a 5-server cluster, if any majority of the servers are available, the whole system will be available, fully operational. So you can lose 2 servers, no problem. You lose the 3rd server, you'll no longer be available, but you'll maintain consistency at all times. And this is key to building consistent storage systems. So any fault-tolerant, consistent system should have consensus somewhere inside of it. If you peek inside at these systems, you'll usually see 2 different things. You might see a to-do that says, this looked hard, so let's leave this for later. Eliminate this single point of failure sometime later. Or worse, you might see some sort of ad hoc algorithm where consensus looked too hard, people kind of try, approximate it, and you end up with excuses like this case is rare and typically occurs as a result of a network partition with replication lag, something that never happens in the real world. Or in a properly built system, at some level you'll find a consensus algorithm. So either Paxos or Raft or Zab. This might be built into the system, might be a library, it might even be a network service. So Zookeeper is quite popular here, where you access a network service that provides the consensus you need and don't have to complicate your own application. So consensus, you typically use it to build what's called a replicated state machine, and it's a replicated state machine that you then use in your larger system. This is kind of the replicated state machine architecture, where by state machine, what I mean is just some data structure that you want your clients to interact with. And here I'm showing kind of a simple map, like x to 1, y is 2, something that'll change over time, deterministic. And then, so I'm showing a cluster of 3 servers here, where each server has its own copy of the state machine, but the system as a whole is going to provide the illusion that there's just one coherent state machine. So each server has its own state machine. Instead of taking commands to modify that directly from clients, the state machine each state machine plays commands from a log. So first apply x gets 3, then y gets 2, etc. The idea is that if all the logs on all the different servers look the same, and have the same series of commands, then all of the state machines will end up in the same state and produce the same result for clients. So that's how you provide the illusion of a single system. And it's the job of a consensus module to ensure that, to ensure proper log replication. So to take commands from clients, to order them consistently into the log, and to persist them there. So for most of the talk, I'll just focus on providing a replicated log. The state machine's really kind of the application on top. And as I mentioned before, the system will make progress as long as any majority of the servers are up. That's for a typical algorithm like Paxos or Raft or Zab. And it can handle servers coming and going, messages kind of being arbitrarily delayed or lost, but no Byzantine failures, so servers can't lie to you. So then, how do you use replicated state machines in a real system, well, there's kind of two categories for this. One would be use it to manage your top-level system configuration, and the other is to replicate an entire database state. So here in the top-level system configuration, you'll have exactly one replicated state machine, and it might manage things like what servers are in the cluster, what shards of my database does each server have, or what part of the namespace is each server in charge of. So on the left, you can imagine a system where most of your cluster, or all of your cluster servers just interact directly with the replicated state machine to communicate. So maybe they're pulling work off of a work queue, and that work queue is the state machine. On the right, you see a common simplification where you want some active entity to manage your cluster, but you don't want that thing to be a single point of failure. This is actually, this is my use case. So I started Raft as part of RAM Cloud, and we have a single cluster coordinator that, if in the past, if it failed, that was it for your whole system. So instead, what we do now, store all of that the critical coordinator state in a replicated state machine, and then there's standby coordinators that can be elected and pull that state out if they need to, and then they can take the role of coordinator. So a very different approach is if you want to take all of your database state and manage it using consensus. So this is the approach taken by Spanner, Megastore, HydraBase, where you kind of partition all your data and you assign each partition to a replicated state machine. And quite often, some of the members of each replicated state machine might span the globe. So that has the advantage that kind of each partition can autonomously recover from failures and without any involvement of some central authority. And if you need to undergo operations across partitions in an atomic way, you can kind of use a two-phase commit protocol pretty simply because you know that none of these replicated state machines will fail, or it's highly unlikely for them to fail. That's kind of how replicated state machines are used in practice. Now, getting back to the details of how they're implemented, historically it's been the Paxos protocol that's basically synonymous with consensus today. It was created by Leslie Lamport, this year's Turing Award winner. And unfortunately, there's two key problems with Paxos. I'll summarize them using these quotes. So an NSDI reviewer wrote, "The dirty little secret of the NSDI community is that at most 5 people really truly understand every part of Paxos." Wink. As in, Paxos is really hard to understand. Even one of the top systems conference full of academics, we don't get it, and it's a fundamental protocol for distributed systems. And then the Chubby authors, so Chubby is a replicated state machine inside of Google. They wrote, "There are significant gaps between the description of the Paxos algorithm and the needs of a real-world system. The final system will be based on an unproven protocol." So not only is this thing really hard to understand, it's actually really hard to implement in a real system. These are the problems that we tried to address with Raft. We designed Raft specifically for understandability. Our goal was to find the best algorithm for building real practical systems. So it had to be correct, had to be complete, had to perform well. These are things that Paxos already did, but it also had to be understandable so that you could teach it and so that you could implement it at a reasonable cost. And then at every step of the way, when we reached a design decision, we asked, well, what would be easier to understand or what would be easier to explain? And that's kind of the criteria we used to explore a new design. What we ended up with is a fundamentally different decomposition from what Paxos does. So Raft relies pretty heavily on a leader, whereas that's kind of an afterthought in Paxos. The algorithm has less complexity in its state space, so it operates in a more restricted form, which makes it simpler to understand. And overall, it just has much less mechanism. So you'll see in a minute how Raft is actually quite compact. These things again lead to easier to teach, easier to implement. So on the teaching, we actually did a study to compare, is Raft actually easier for people to understand? I don't have time to get into the details of the study, but basically we took a classroom of students at Stanford and another classroom at Berkeley, and we taught them both Paxos and Raft using some video lectures. You can actually find these on YouTube. And on the left, you can see we quizzed the students after, and 33 of the 43 students actually scored higher than Raft after spending about the same time learning it. And then on the right, we asked them, if you had to implement one of these, or you had to explain one of these to a fellow student, which one would you choose, Paxos or Raft? And nearly everyone said Raft in that case. So it's really encouraging for the understandability. As I said, I don't have time to get into the details. I think what's more important to do in this talk is to try to just teach you Raft, and you can then decide for yourself. So I'll be using a visualization to do that, but first kind of an overview so that you're not too lost. So Raft is split up into 3 parts: leader election, log replication, that's kind of what happens during normal operation, and then safety to tie these things together and actually create a consistent system. So in leader election, the idea is to select one of the servers to act as the cluster leader. And if that server were to go down, we want to detect a crash and select a new leader to take its place. In log replication, it's that leader's job to take commands from clients. These are the commands that are ultimately destined for the replicated state machine. Append those commands to the leader's log, and then make the other server's log match the leader's. So the leader will replicate its log to the other servers and override any inconsistencies. The third section is safety, so we add a restriction on leader election here so that only a server with an up-to-date log can become leader. And given that, when the leader replicates its log to the other servers, and the other servers just override any inconsistencies, that actually is safe since the leader's log is actually known to be good. Let me flip over. Okay. So this is going to be a little fast. Feel free to pause me, but I can't really go back. So leader election, keep your eye out on server 2. It's about to time out, start an election, and become leader. So there it's timing out. And now it's leader, and its first job is to send a round of heartbeats to the cluster. That was a full leader election. It happens in 1 round. That was a little too quick to understand, so I'm going to go into it in more detail now. So you'll note that this server is leader in term 2. Terms are used to distinguish leaders, newer leaders from older leaders. So it's kind of a logical clock. So I'm going to crash server 2 now, and you'll see server 3 become leader in term 3. So server 3 first times out and increments its term to term 3. That's the number here, and also the pink color. So you notice that the other servers are still on term 2. That's because we're in a distributed system here. We're not nothing can happen atomically across the whole cluster. And so these servers will stay in term 2 for now, but every message that's sent in Raft actually includes the sender's term number, and the recipient will adopt the largest term number it's ever seen. So as soon as these other servers receive these messages, they will also adopt term 3. Okay, and you see these dots around server 3. Those represent votes. So server 3 has entered what's called the candidate state. It's trying to become a leader itself. And to do so, it needs to collect votes from a majority of the cluster. Servers are kind of greedy, so the first thing they do is vote for themselves. That's why it's already got one dot filled in. And so these messages you see, they're called request vote RPCs. And so the purpose is for server 3 is asking the other servers, please can I have your vote? Okay, so fast forwarding just a little bit. Now, these 3 other servers have received the messages, so they updated themselves to term 3, and they all voted for server 3. It's the plus sign you see. So the server's allowed to vote at most once per term, and for now it's just going to vote first come, first served. So as soon as server 3 learns that it has received the majority of the votes, then it'll become leader in term 3, and its first job as leader is to send out a round of heartbeats. There are the heartbeats, and that leader election is done. Okay, so those 2 were like good normal case elections. That's what you would expect to happen 90-95% of the time. What we needed, though, was for one of those servers to time out ahead of the others. So if that doesn't happen, we've got what's called a split vote, and I'll show you that now. You'll note server 1 and server 5, they're about to time out at the exact same time, and they're going to campaign for leadership in term 4. So they're both candidates now, and they both voted for themselves, and they both broadcast out their request vote messages. Unfortunately for them, it just so happens that each of them reaches one of the other servers first, so each of them is actually only going to collect one more vote. That'll leave them with 2 out of 5 votes, not enough to become leader. So that's kind of unfortunate. You can see they're trying to get server 2's vote, but I killed server 2, so that's not going to work. So now server 1, server 5 are kind of stuck in this candidate state. The cluster has no leader. What do? Well, in Raft, we do the simple, stupid thing, which is just wait for another timeout to go by. And in this case, you'll see server 3 actually times out in term 5 and is able to collect votes in term 5 and become leader. So how do we kind of encourage that behavior? Well, we randomize those timeouts. So it's not, it's not that all the servers are synchronized using the same timeouts. In fact, when they reset their timeout, you might have noticed it resets randomly somewhere between halfway and all the way around the circle. And that gives the servers enough of that creates enough of a range that it's highly likely for one server to time out first. Actually, less so in this visualization than in a real system. So normal case elections would proceed in just one term. The ones that don't will typically just result in one split vote and then will be resolved quickly. And that's it for elections. Yep. So we developed it for a LAN. The same concepts apply to a WAN, but you just might need to scale the timeouts. So maybe can at a first approximation, you're right. Let me hold off on comparing with Paxos and Zookeeper to the end of the talk. Like I said, I'll come back to leader election and change it slightly later. Okay, so going on to log replication. So you can see this thing on the right. That's the logs in the cluster. So it's again a 5-server cluster, but I've actually killed off 3 of the servers so that they're not in the way. So we're just focusing on servers 1 and 2 right now. Server 1 actually became leader, I guess, sometime before I killed off server 3, and a client came up to server, or 3 clients came up to server 1, and they each asked the leader to please, here's my command, please apply it to the state machine. So the leaders ended up with 3 entries in its log. This is the leader of term 2, and when it receives an entry, command from a client, it'll create an entry and write its own term number in that entry. So that's why these entries are all blue with term 2 in them. So let's go through log replication. I'll allow server 1 to just replicate that first entry. So now server 2 has the same entry. Let me explain the dot and the arrow. So the arrow is called the next index. This is the position in the log where the leader will send the next entry to that server. And to make progress, you want that to be, the point where they diverge. And then the dot is the match index. And that means that the leader knows that it and the follower agree all the way up through the dot. So here, they agree up through that first entry, and the leader knows to send the second entry next. That's actually what the message is about to do. So you can see that proceed. The visualization goes 1 entry at a time, but you could tweak it to do batching pretty easily. Okay, so now the leader and server 2's logs are identical. You notice these entries still have dashed lines around them. That means they're not committed yet. They're not yet necessarily durable. So those commands haven't been acknowledged to clients yet. You can imagine, to give you an idea of the kind of thinking you need to do, you can imagine if server 1 and server 2 were to go down, servers 3, 4, and 5 came up. Well, 3, 4, and 5 don't even have a copy of that entry, but they could elect a leader amongst themselves, and those entries might be lost forever. So that's why they're not safe yet. To make them safe, we actually have to replicate them to 1 more server. So I brought up server 3, and now the leader has replicated that first entry to server 3, and the match index has gone up. So at this point, the leader has marked the first entry committed in its own log, and a leader gets to mark an entry committed that it created once that entry has reached a majority of the cluster. So here, server 1 knows the entry is committed. The other servers actually don't know it yet. You notice that the same entry is still dashed on their servers, in their logs. And so the leader, actually part of this replication RPC is called append entries. Part of the append entries RPC is to include the commit index. So this message down to server 3 is going to inform server 3 of the entry's commitment, and the next message to server 2 will do the same. If you let this advance for a while, you'll see we get replication 3 waves out, and eventually everyone learns that every entry is committed. So that's great. That's kind of normal case log replication. And now let's get into the somewhat harder cases. So There's two inconsistencies that can arise because leaders go up and down and switch over. So you can have missing entries, and you can have extraneous entries. And I'll go through both of those. Same cluster, but I fast forwarded quite a bit. So let's see. Server 1, it used to be our leader. Had a couple more clients come up to it and say, hey, please replicate these entries. Before it got a chance to do that, though, it failed. And then server 4 came back up, and server 2 is our new lead. So now server 1's down for a while, and it's got those extraneous entries that we'll get to later. But first, missing entries. Server 2 is now our leader, so you know, what's the difference between the leader's log and the leader's log? It's kind of trivial. But actually, while we're here, so you can use the concept of the match index on the leader to record how far the disk has gotten in persisting entries. That's actually a pretty useful optimization. Okay, so server 2, our leader, has initialized all the next indices to be just past the end of its log. You'll see that works really well for server 3 and not so well for server 4 that's missing 3 of these entries. So on this first heartbeat, you see server 3 replies positively, server 4 replies negatively. What's that about? Well, append entries includes a simple consistency check. So if next index is pointing at index 4, then the append entries will say, hey, do you at index 3 have an entry with term 2? So the leader's kind of looking to see if the prior index matches in order to build an induction. So server 3 says, why, yes, I do have an index with term 2 there, whereas server 4 says, no, I don't. So for server 3, we're going to see this match index advance all the way up. And for server 4, instead, you can see the next index decrements down. Finally, they agree on the empty log, and they build their way back up from there. Okay, so fast forwarded a little more now, where I had submitted a request to server 2, and that request actually got committed on servers 2, 3, and 4, marked committed everywhere. And now I brought back server 1. So you kind of see the trouble here. We need to preserve this pink entry because it's committed. We've told clients that it's going to stick around forever. And yet server 1 has these extraneous entries that never got acknowledged, aren't really important, but they're in the way. So what happens is, when server 2 sends its append entries messages over to server 1, well, they include that same consistency check, and server 1's just going to overwrite the entries that are in the way. So it kind of has a built-in assertion that this index 3 is going to match. And given that server 2 is the leader of a higher term, so it has more recent information, server 1's just going to truncate the end of its log and override all that information. So now we've resolved those extraneous entries. Yeah. So the match index is just initialized to 0, but it jumps forward quite, pretty quickly. So for a brand new leader, until you figure out where the logs diverge, you won't be able to commit any new entries. But That's a pretty brief period of time. We'll consider like server 5 in this case doesn't actually have those committed entries yet. I guess it wouldn't affect the operation of the algorithm in any way. Yeah, so right, so I guess I didn't say each server state machine applies as far as the last committed entry and no farther. So server 1 would not have applied the dashed entries, and all of these servers would now apply all of the entries. No, so it's only the leader that decides when entries are committed. They're just they don't until an entry is committed. It's only in the log, and it's persisted to disk, but it's not. It won't affect the state machine, and it won't be externalized in any way. We can come back to that later. Okay, so we've gone through log replication, both the normal case where kind of in this situation where everyone's next index is pretty well aligned, takes one round trip to half the cluster for the leader to commit an entry. And now I'll move on to the third section on safety. So let me start by motivating the problem. Same cluster, but I've killed server 2 and brought up server 5 again. But wouldn't it be bad if server 5 happened to time out first and try to become leader? The problem is server 5 has a completely empty log, and if it became leader, it doesn't know that there's all these committed entries out there. It might just replace them with entries of its own, and then all consistency would be lost. But what happens is when it becomes candidate and it requests votes, those request vote messages actually include information about the candidate's log. And a server won't vote for a candidate whose log is less up to date than its own. So in this case, server 5 isn't able to get any votes at all except for its own, so it can't get the majority needed to become leader. Instead, what happens is, again, we wait another timeout. Server 3 will time out for term 5 and become leader in term 5. And its log is eligible, so it can collect votes as normal. But what exactly is that rule, that information about the candidate's log? Well, it's the length of the log, but more importantly, it's the term of the last log entry. So the terms so here term 4 is the more significant bit, where this top server would not vote for the middle server because the term of its last entry is larger. And the middle server wouldn't vote for the bottom server since the middle server's log is strictly longer. So when you take that rule in aggregate, what it gets you is that if you don't have all the committed entries, then you can't become leader. So any server that goes through the candidate phase and is able to collect a majority of the votes already has all the entries we care about in its log. And that's what makes Raft safe. Let me flip back to my slides. So to review the things we covered there, in leader election, the cluster uses heartbeats and timeouts to detect crashes, and these timeouts are actually randomized so that we can avoid split votes. The majority voting guarantees that we've got at most 1 leader per term. It's kind of a key property that you need to maintain consistency. In log replication, you saw how the leader can take commands from clients and append them to its log, and then replicate its log to other servers. Those other servers will just overwrite any inconsistencies. There's this built-in consistency check with the term of the previous entry, which is used to make sure that logs don't diverge in funny ways. We can't possibly create a mishmash in Raft. If 2 logs have the same entry in one position, then the entire prefix before that will also match. And then in the safety section, we tied that together so that only leaders with all committed entries in their logs, we can only elect a leader if it has all committed entries in its log already. And then when it does overwrite inconsistencies, that's actually safe. One thing I touched on but didn't go through the example was that I said a leader that creates an entry can mark that entry committed once it's replicated to a majority of the cluster. New leaders in Raft actually, if they inherit entries from prior terms, they won't commit those right away until they're able to push one of their own entries out. You can see the paper for the example on that. Kind of take some time to walk through. Ooh. Yeah. No, the absolute last one in their log, even if it's uncommitted. Right. Absolutely. And there's sort of always that potential in a distributed system that you actually do some work and then the acknowledgement gets lost. Except in Raft, it can, I guess, happen in the other direction. Or no. I mean, what can happen is the cluster moves on and yet later actually does the work, but it's kind of too late to acknowledge the client. You cannot roll back a committed entry. Uh-huh. Right. So now, there are some rare cases where that one could still be rolled back. I think. So just conservatively, if something's committed, then we will absolutely keep it for all time. If it's not committed, don't know. The way you decide is there any possibility that a server could become leader without having that entry? Next slide, I think. So the question, it's a fun benchmark I'm showing here. Question was, how often are these split votes going to happen? How much randomization do you need to avoid them? So I tried to create the absolute worst case situation. On a gigabit Ethernet LAN with 5 servers, just try to synchronize those servers with using heartbeats and then have them time out at, instead of choosing randomly, a fixed 150 millisecond timeout. And if we do that, then basically every election takes longer than 10 seconds. So just going through, what is that, like 60 split votes at a minimum per election. If you give the same cluster just a little bit of randomness, that's really all it takes. So we'd recommend something conservatively, like choose the timeouts randomly between 150 and 300 milliseconds. And then basically all of your elections will complete within a couple hundred milliseconds. And the fraction of elections that have split votes is down here in the 4% or so. Of those 4%, 96% will complete in the next term, etc. So it converges quite quickly. Does that answer your question? Right. So it's not the one with the highest term. It's one that is highest compared. That's backward. It's the majority of most suitable logs that could become elected leader. So of any 5-server cluster, at least 3 of them will always be eligible. But it's right. Right. So under asymmetric network partitions, I won't guarantee availability. And if you do want to operate in those cases, there's some things you can do to the protocol to make it a bit more robust. You see my thesis for that, but it's really, the hope is that you have bidirectional communication, and if you don't, can't really make guarantees. So going forward, it's hard to evaluate kind of how easy Raft is to implement, but one piece of evidence I do have is that there's dozens of implementations in progress. Some of these are at companies, some of these are people in their spare time. Not all of these are production ready by any means, but the paper was just published in June for the first time, so it's these guys got a head start, but it's still pretty early. And you can see these are in a wide variety of languages. I think that's because the people doing it in their spare time pick their new favorite language to use. Some of these, like Go Raft, are libraries. Some of them, like Log Cabin, which is my implementation in C++, are kind of full-blown network services. And another one I wanted to touch on is Facebook's Hydra base. I think they're the first example of people kind of using Raft for replicating entire database state. And they're doing so in a cross data center way. The image I stole from them seems to be hard to read on this projector, but the idea is they would take, here you've got 3 different data centers, and they want to create a consistent view of HDFS. And so they're actually showing 5 Raft servers, 5, and some of them are, and their state machine in this example is HDFS. So some of their Raft servers actually don't have state machines. I think that's because probably running a full-blown HDFS node is expensive, but they do participate in the log replication so that they can be relied on in case of a crash. So these 2 data centers they each have 2 servers in them, but only one state machine, and then this data center is just purely for replication purposes. Actually, I don't know much about any other deviations they've made from Raft, but I thought I'd throw this out there in case it comes up in the Q&A. So to wrap up the talk, consensus is needed for building all these consistent storage systems, but until now, at least, it was widely regarded as difficult. Paxos, really hard to learn, really hard to implement. So we designed Raft specifically for understandability. The user study showed that it's easier to teach in classrooms. We think it's a better foundation for building practical systems because it's a lot closer to what it, the replicated state machine, replicated log approach, which is what you actually want in a system, has better problem decomposition using a strong leader, and a lot less mechanism. Those 4 messages, the request vote, request and response, and the append entries request and response, get you through the entirety of the core algorithm and cluster membership changes. There are quite a bit there's several more topics that you need for a full-blown system. So cluster membership changes would be, say I start with a 3-server cluster, and I change my mind up to a 5-server cluster, or how do I replace servers if they fail? You actually need to do that through the consensus algorithm because you're changing the definition of majority. So to do that safely, you want to automate that. Log compaction. Well, what do we do when the Raft log grows too big? Can't keep just appending commands to it for all time. So the tech report goes through kind of a snapshotting approach, and that's generalized in my thesis. So you can do things like level DB or SS tables. Client interaction is actually often overlooked, but it's a source of bugs. Is how do clients interact with the system, get the consistency guarantees that we actually want, and especially how do you implement read-only operations with the same level of consistency. And then, of course, there's more evaluation that I didn't cover here. All right, I'll take questions. And there's a mic, or I can try to repeat your questions.
Can you compare at the high level how this is different than, like virtual synchrony, extended virtual synchrony? Because I see a lot of difference in there.
I cannot. No, I'm not really familiar with the virtual synchrony work. I think there's some claim that there's equivalence to consensus there, but no.
Yeah, because from there, what I remember was that for each of the election, they bump up the terms, and so that
right. So the idea of a term number, I can say, is it's just fundamental to the problem. So Paxos calls it a proposal number, Zookeeper calls it an epoch, ViewStamp replication calls it a view, but this idea that we're not relying on actual wall time here to decide who's stale and who's current. So you need to somehow propagate that around using a logical clock. And in all of these algorithms, once you adopt a higher number, you're going to start either ignoring or rejecting messages with a lower number.
Thanks.
I may be misremembering, but I thought when I first saw this work a year ago or whatever, there were some blog posts. Did you guys use TLA Plus to verify some of this, or am I misremembering?
Yeah, so I have a formal spec written in TLA Plus. I also tried to use some of the TLA proof system to automatically prove it, and then backed off and did more of a Englishy proof. But
Is Englishy a technical term? I'm kidding.
What I
so What prompted the back off then? Like, I saw the list of other stuff in your thesis and tech report, like membership change, compaction. Was it the core algorithm you backed off, or was it when you started to add all these features you need to be real that you backed off?
No, it was even in just the core algorithm. So I got up to like 4,000 lines of TLA proof, and it was unmaintainable. And part of that might be my failing, like have no training in formal methods. But I think part of, like, I don't know that that's the best tool for the job. One example is, like, there's no type system in TLA. So kind of every step of the way, you need to say, yeah, I added one to that, so it's still an integer. And only then can you actually get the tools to agree with you. I discussed that in the correctness chapter in my thesis, if you want to read more.
So 2 questions. One is, I see similarities and I don't really see any specific differences with ZAB. Is that something that you can touch? Anything that is outstanding? I know that it's more or less similar at a very high level, but I want, like, is there something really specific that it differentiates from ZAB?
Sure. I think, at a high level, kind of view-stamped replication, ZAB and Raft are pretty close. At kind of a low level, because we did push on understandability so hard, you see that, like, Raft has 4 message types where ZAB has 10. So it's just kind of, if you're pushing on understandability, you need to motivate every piece of the algorithm. And if there's something you can't motivate, that's probably because it shouldn't be there. I don't want to, Zookeeper's really widely used. It seems to work. It appears to be correct and everything. I don't want to say anything too bad about them, but I think it's one difference is, like, the academic approach and the industry approach, where we were trying to find an algorithm that optimizes understandability. They were trying to find an algorithm that works.
So the other thing is, you did mention about the clients. So is there anything special that is being done here in terms of how to guarantee? Because one of the real problems that we found with Zookeeper is it's very hard to, in some cases, to make sure that a write was successful.
Right. So, I mean, a lot of that does fall on implementations and how they expose their APIs and stuff. One thing that I think is particularly hard about Zookeeper is that if you're disconnected from the server you happen to be talking to, then kind of all information is lost. So at least in my implementation, I've tried, like, sessions are a concept that's shared across servers, and so the client can reconnect that way. This is stuff Zookeeper could do, but
for the clients as well. How to implement a client, or is it mainly?
No, not even, not a TLA spec or anything. I have a chapter describing it.
I see.
My thesis. I have code. Yeah. Go follow that. Yeah, so there's dozens of implementations of Raft in progress, and dozens that are permissively licensed. That's excluding Hydra-base, but everything else I talked about.
Another question? Cool, thank you. So we'll be having lunch. So if you're interested in further questions about Raft, then you can join.